Good afternoon. Welcome to Cambridge University Botanic Garden. I'm Michael Perry.
And I'm Ellen Mary.
And we are from the Plant-Based Podcast. And today we're doing a bit of a takeover at the garden.
Yay.
So there's a brand new exhibition called PlaMatSu, and it's all about plant surfaces, colours, and how they can be applied in day-to-day life with materials and the like. So let's delve in a little bit more, but first up, Ellen's got a little bit of housekeeping.
So cool. I cannot wait to find out more about plant-inspired surfaces and materials. But first, I think we should really know who's who and what's what. First of all, there is no fire alarm planned. So, you know, if you hear anything, then we're going to be running away. Behind the camera is actually Helen, and Helen's going to be there to pass on all of your questions when you ask them. And we are bubbling with our little plant buddy little bubble, aren't we? And inside we're going to meet Silvia, who is a physicist, and what she doesn't know, it's absolutely fascinating, so I can't wait to delve in.
Absolutely. We'll be at a physical distance with Silvia, but we'll be close enough to get all of those all-important answers to your plant questions. So don't forget to comment down below, ask any questions, and if there's any problems with sound or you can't see us or anything goes wrong, just let us know down below and we'll address it as soon as we can.
Let you know down below?
Yes. Cool, let's go in.
Hello, Silvia.
Hello. Hi.
This is Silvia, everybody.
Hello.
So this exhibition has been running, hasn't it, since the beginning of September?
Yes.
And when we came along, I wasn't entirely sure what to expect, but I'm so fascinated already with everything I can see. So really, really excited. And you've got different stations, haven't you?
Yes.
So we'll start off with this one, which is all about nature's colour.
Yes.
But tell us a little bit about, you know, what the exhibition as a whole is all about. What is it here to inspire and to discover?
So this exhibition is about a European project that many different groups were participating, and the main aim was really to bring together physicists, chemists, plant biologists in order to understand how plants make their own materials, but also how we can then take inspiration from plants to make material that can find use in our everyday technology, but more sustainable, because then we really aim to use same material that comes from plants, so cellulose like cotton, and then you will be amazed of what you can achieve with the same type of structure.
Like plants are so cool, aren't they?
I know. So here we're going to look at some colours. This is iridescence, because blue is not always blue, is it, Silvia?
Yes.
So blue in nature isn't real, is it? Am I right?
No, it is real.
Is
so
a real colour?
Yes, you have it. You have it also. So real color, you generally might say real color, the color that comes from pigment, the same pigment that we use to dye our clothes, or maybe we use to paint like a wall, right? So these are color that you might call them real color because they are obtained by a mechanism which is called absorption. So you have the sunlight. Part of the light is absorbed by the molecule, so depends on really of the material itself.
Yeah.
And part of the light is reflected, and that's the color you perceive.
Okay.
So, but there are another class of color that this is what you refer, that they look glittery, iridescent. So this type of color are not a property of the material, but are a property of the structures. It sounds weird, but if you think about a soap bubble, as soon as you have the liquid, it's totally transparent, right? But as soon as you make the bubble, so you have a really thin layer of water, and this thin layer can interact with light with a completely different phenomenon. It's called interference.
Yeah.
And then if you really are able to manipulate material on that scale, you can create color in this way, and then you get the color that are really like really shiny, metallic. They have this metallic tint, and also can be actually iridescent, so that the color look different depending on the angle that you are.
Really, all you need in your life is a physicist. That's all you need to describe everything.
kind of.
So Silvia, why do the plants do that then? Why do they need to have this iridescence on their foliage, for example?
This is a huge question.
Yeah.
So and there is not a unique answer. So it depends on the context and depends on the plant. And that's also the beauty of plants, because you have so many, and then each of them has spectacular properties, and then they might have completely different function. So the same blue that you see in some ferns, in some plants, for example, what we think is that what is happening in Salaginella, they are used to reflect UV blue light that can be damaging, so it's a photoprotective mechanism. The same way we put sun cream on the tiny leaves, the one that they are growing, so the younger leaves, you have this protective layer that can reflect this harmful light.
So it's almost a plant that grows in the shade but has got used to growing in the sun by protecting itself from the UV rays.
So you depends on also where they grow, so this kind of phenomenon can happen or not, it can be more visible or not, but this is all not fully understand, so just taking it with a pinch of salt. In other plants like the begonia, for example, you still see blue, but in that case it seems that it's not used for photoprotection, but actually it's exploited to improve the light that enter the leaves and then to boost photosynthesis. It's really different from system to system, and actually each of them you have to study in order to understand what's going on.
Wow, your coat's very slightly iridescent.
I know, I'm iridescent myself.
Yeah, you're just like a morpho butterfly.
Can we look at a couple of examples of that? Because I know you have got a berry that's
iridescent. Yes, so one of what I like most, so that's my favorite blue, are these blue that come from these different berries. This is an example, but there are many others. There are many others. So these are called Margaritaria nobilis. If you come to the Botanic Garden, there is also a tree.
Is that outdoors?
Yes, no, it's indoors.
So it's a tropical plant.
Yes, a tropical plant. This one, they come from Panama. And what is nice is that this color here is made out of cellulose. That is the same material that you have to use paper, right? And textiles. So what does the plants do? It's pretty crazy. You have fibers, like the fibers of your cotton, but then if you really go inside the cell wall, these fibers are really, really tiny, only a few nanometers, and they can organize in this architecture, which is called the helicoid. So you see this, you have fibers that go in one direction, then every layer, you have different layers, and in this layer are twisting, and when this distance is comparable with the wavelength of the light, you can get color. So similar to the soap bubble. So what you want to have is that the size, the average size of this material where you have this layered structure is comparable with the one of the light wavelength. So if you compress it, you get blue, and if you kind of swell it, you can get red.
Yeah. Wow.
So
my mind is blown here.
I think it's pretty amazing by itself, because it's kind of we still don't know how, for example, plants can control to this level of sophistication on this length scale, creating architecture that are pretty regular, then they look like this.
How do they know?
We don't know
how to do that. That's the kind of science that we haven't discovered.
That's what we are working on, but we still didn't get there. In several years. So it's complex, because you have many material that interact, and the way they interact, it's challenging to understand. But what we can do already, I think it's pretty cool. We can really copy what we have the architecture here. Yeah. So you can take cellulose, you can isolate it from wood pulp. That is also the same, you make papers, but you can also take it from old textile or from mango peel, banana peel. So all waste material that is rich in cellulose. Yeah. And if you know how to do it, you can actually recreate this color in the lab. So these are cellulose film that, instead of looking transparent, right, they have the same structural color. But this is pure cellulose, so you could eat it.
So the important question for me is, how can we translate that to everyday materials? What can we learn from this plant?
So, for example, this type of system, what we want to do, we are really trying to use them as pigment. So to replace commercial pigment formulation or commercial glitter, but with the advantage is that at the end, once you have this, once you are able to make it, this is 100% cellulose. So once it goes in the environment, is not anymore. It's not
organic glitter.
Yes, it's 100% organic glitter. And actually, if you keep it in water, and you just leave it outside, it starts to become moldy, because it's essentially degraded.
Wow.
Okay. So it's not like it does. What is glitter now? You have it plastic or inorganic material. Yeah. So this one, it's really not harmful.
I wonder what the easiest to grow iridescent plant is that we can grow at home in the UK.
So I think that the begonia is that.
Yeah, of course.
You buy them. Yes, the begonia you can buy them. There is another one is called Macrosorum. Also the Macrosorum, it's something that grows, and you actually grows pretty well. We were able as well to grow inside the polia. It works pretty well inside. If you get the seeds, it's working. So they are not difficult to grow.
Everyone's going to be looking out for this begonia now, aren't they? Everybody. What have we got at the next station over there? They're moving on.
Don't forget, you guys can ask any questions at any time. If you're wondering anything about the iridescence or anything that you see coming up, then drop the question down below, and Helen will feed it through to us.
She will.
So here we change a little bit gear, and we change topic, and then we look at the surfaces.
Okay.
And we look at surfaces of the plants. So we don't care anymore about the color, but just look how they feel and what can you get out of a surface. And also here I think it's pretty exceptional, because you might not think that plants can do something special, right?
Yeah.
But already the ability, to stand outside with that, like with the horrible weather without getting soaked, you need to have material that are good enough and they are able to repel water. And especially plants that lives on water. So you think about the lotus leaf, right? It has properties that are really impressive.
The one that's looking at you all of the time, basically, that one. The one that looks like it's got all the little eyes.
That's the lotus leaf. Trypophobia, isn't it?
If you are able to produce material that have the same type of property, you might say, why are they useful? So at the moment, for example, Teflon or treatment that you have on your car screen when they clean your car, car wash, sometimes they can put a layer of material that makes
like
the screen that makes the screen that doesn't wet that easily.
It's a repellent.
So that repellent, so that the water just drop away without having you to clean. And in fact, these are called also self-cleaning material. Or you also have it in your glasses often. That when you have the droplets don't stick. So at the moment, this type of material is made out of inorganic particle or small nanoparticle. But the plants can do it with, again, natural polymer. So a natural material.
And plants have been doing it for years.
Yeah, they've been doing it a long time.
And actually, I think it's like people have taken inspiration, and the way that the plant can develop such we call them hierarchical structure, because you have structure that are on the nanometer scale, structure that are on the few micron, and then they are macroscopically big, right? So you have complexity on different length scales. So if you think about manufacturing something like this, from a point of view you make it in a company, it's really challenging, because it's difficult to address all these different scale at the same time with the precision that you have it in plants. So this is, for me, it's one of the most fascinating things.
And you've got one of those examples here with the salvinia.
Yes.
Haven't you?
Yes, and the salvinia is particularly crazy in terms of performances. In fact, it works. It's so hydrophobic that that could, but it also has the property that you could actually use it to remove oil from water. So they are developing materials that they can be exploited to oil spillage in the ocean.
Wow!
Because then they are really able to absorb selectively oil. And this is just a property of the surface, of material surface. So
it's quite incredible how much science is going on behind the scenes. We don't often see this stuff happening, do we? We don't know it. We want there to be solutions, but actually scientists are working really hard on trying to find out how plants can really help us in a sustainable way.
Yes, and what is the main point is really trying to use the material that then at the end are not damaging. If you really use that. I think
so what's this station over here? This looks really fascinating. It looks like we can actually get our hands into
you
stuff
would ask plants at the end, they do this not because for us scientists, but because there is a function into that, right? So water repellent is because if you are a plant that lives in the water, you don't want to get soaked wet. But they can also use it as a defense from insects, from pests. So the plant. So in this case, for example, in this you have different surfaces, and they are magnified at different. So otherwise, you wouldn't be able to feel them if they were really on the same scale.
Yeah.
And on the plant, generally, these surfaces are of the order like few microns, so the same thickness of your hair.
Right.
Yeah. Or even smaller. And depending on the surface morphology, insect can easily walk on them or not. So if you try it, like if you start from the first one, they are flat, so you shouldn't feel anything particularly.
Don't be scared.
It feels like I'm a celebrity. Get me out of it. You know where they put their hands in the boxes and it's snakes or spiders. That's what I.
No, no snake. Only plastic
Only
demonstrators.
You know, plants are so tactile. You know, and it's so good to touch them, and you know, and actually kind of really feel and sensation, because it's good for your well-being as well, isn't it? But obviously we can't feel this
in the same way
as an insect.
Exactly,
will feel
because you have to think about the insect legs are really tiny, right?
This is like
so you
Velcro.
have to, yes. In that one actually the insect get trapped and then they cannot really stick. So it's a mean plant.
What
can we learn from these surfaces when it comes to materials in the home?
What we want to try to do, and this was one of the projects of this program, it was actually to try to make material that have the similar characteristic of natural plants using cellulose. So if you have this really wrinkly type of surfaces, insect cannot go through. So this is a sort of an anti-repellent system naturally made by the plant themselves. Okay. So we are trying to make them similar material again using polysaccharides, so that you can use that to spray on other plants as a insect repellent, but without having to use pesticides, chemicals.
Okay,
so you will use like a physical method to get rid of
using plants to help plants.
Definitely.
Yes. We like that, don't we?
Now there's one final thing that we must show everybody, because I've just learned how the tulip queen of the night gets its colour. I thought it was black or dark purple, but that is another iridescent flower, isn't it?
So the dark coloration comes from a pigment, so you always have a pigment underneath. But then on top of the pigment, again, you have a surface modulation. And in this case, the surfaces are really tiny ridges. And we have here all this CD, because at the end, the ridges that you have on the surface of these flowers are analogous of what you have on a CD. So the same reason you see this funky effect of multicoloration on top of a CD is exactly the same that you see it on the tulip queen of the night. And this one, now we are really happy that we discovered that actually has a signaling function with bees, so it helps bees to spot the position of the flowers. And what many people also here in the network, and essentially Beverly Glover, she in a research group is actually working on trying to understand how genetically the structural color is regulated. So how can you genetically engineer a flower in order to have this special feature?
You know,
true blue rose. There you go.
One day maybe. Keep looking for that. You know, there is so much more to find out, isn't there, about plants, and we've really only touched the surface, haven't we? So thank you so much for everything you do and all the research, and for showing us around here today as well.
No problem.
Fascinating. And you know, next time you look at a plant, touch a plant, you know, study the colours in the surfaces, just think how important they are.
And if they have funky coloration, contact us. That we will have a look at them.
Super.
We hope that you've enjoyed the live today, and we must say, I mean, we are blown away, aren't we? We just love anything to do with plants, but here at the Botanic Garden there's just so much to see. There's also an inspiring design and technology trail that you can come and have a look around. Come and take a look in this exhibition, which is still running until the end of October, and of course it's for free. And don't forget, there's also a cafe, because as gardeners all like tea and cake, don't we too? and also online. Don't forget to check out Cambridge Botanic Garden online, website, Twitter, Instagram, Facebook, you name it, they're there.
Excellent. If you do come along, then drop us a line. You can get in touch with us on the plantbasedpodcast.net. And thank you for listening today. And if you come over any funky flowers, let us all know.